So let's take a closer look at where the electrophile is added on a substituted benzene ring. So I'm going to go back to using anisole, and of course we have three locations that we could add the electrophile to, and I'm going to identify them with three different colors, and then we will follow the reaction at those three different positions and see which one might be more favored than others. So let's look at the first position. We call that the ortho position. That is the position right next to the substituent. And so if I have my benzene ring attack the electrophile, and of course Br plus doesn't exist, I'm just using that to make it a little simpler. We can make Br plus from bromine molecule and FeBr3. So let's look at what we get. So I have that cation, and in this case I have two possible resonance patterns. I could use the lone pair on the O here. I'm going to pause the video and make a bunch of resonance structures, and then I'll come back and we can talk about them. Okay, so here are my 4 resonance structures from adding a generic or a bromine electrophile to the ortho carbon. I have the first cation that's formed. I use the lone pair on the O to make a new resonance structure here. Then I use 2 arrow pushes, to put the cation on the bottom left carbon of the ring, and then I use another allylic cation pattern to put the cation on the bottom right carbon of the ring. So we see that there are 4 resonance structures here. Let's compare that to what happens when we do meta substitution at the green position on our ring here. And again, I'm going to pause the video, draw a few resonance structures, and come right back. So here I have 3 resonance structures. You can see that I added the bromine at this meta position. I made the first cation at the bottom carbon of the ring. Then I used, again, a allylic cation resonance pattern to put the carbon at the upper left carbon, the cation at the upper left carbon. Another resonance pattern puts the cation at the upper right carbon. So I have 3 resonance structures here, and of course I want to do one more set of these, and that's going to be reaction at the purple carbon, where I put the bromine in the para position. And so I'm going to use essentially the same pi bond to put the bromine at the para position. And I'm going to pause the video again and draw these for you and come back in a second. Alright, so here are the resonance structures that result from this purple arrow push and adding the electrophile, in this case the bromine, at the para position. You can see that we formed a cation at the bottom right carbon. Then I used a pattern to push the carbon to the top carbon, the cation to the top carbon, at which point I had 2 options. I could have moved it to the bottom left, or I could have used the lone pair on the O, which is what you see here. I put the cation on the oxygen. Then using these 2 arrows, I can move the cation to the bottom left position. And you'll see that I also have 4 resonance structures now in the para, and I have 4 resonance structures up here with my red pattern for the ortho addition. I only have 3 resonance patterns for the meta position. And so what this tells me is that the para and the ortho, which I've covered up with some arrows up here, is favored. So this is an electron donating group. We learn that it is an activator. And now these resonance structures help us understand why it is favored to add the electrophile at the ortho or the para position. So ortho, para, director. And this will be true of all electron donating groups that are activators. So again, As I've said many times, organic chemists' goal is to have control over the outcome of the reaction. Now we have some control. We aren't just going to get random addition of the bromine at any of these positions. We know that it's going to happen at the red carbon, the ortho position, or the purple carbon, the para position. It will very rarely happen at the green carbon, the meta position, when we have this activating group, this electron donating group attached to the ring. So this is an ortho-para director. One more thing I want to say about this is that if we have an R group that has no lone pairs, so first of all, these are the special resonance patterns that we get with this electron donating group that has the lone pair that can be donated to the ring. You'll see that the other resonance patterns, these three, are pretty typical of what we got even with the green addition, the meta addition, and the para addition. But it's the ones that I've circled in blue that are the extra fourth resonance structure that contribute to the fact that the ortho and the para addition are favored in this case. So now let me look at what happens if we have an R group, just say a methyl group or an ethyl group in place of the methoxide. So here I have a generic R group attached to my benzene ring. In this case I use isopropyl. And I have the three resonance patterns that I would get if I added this bromine electrophile in the para position. The first one here has the cation on the lower right, then I put the cation on the top carbon, and then on the lower left. So those are the standard three resonance structures you'd expect for this, the cation in the ring, often called the sigma complex. Now you'll notice that in this case, this is an electron donating group, but it is not OCH3 like we had on the previous slide. So there is no lone pair that I can use to donate and further stabilize this particular cation here. However, we do still have an advantage having this R group present and adding the bromine to the para position, and that's in the case of this resonance structure. This is a tertiary cation. Otherwise, if there was no R group, it would be a secondary cation. So here is the advantage we have with a simple alkyl group. We don't have a additional resonance structure, but we do get a slightly more stable cation intermediate here. This is tertiary, where otherwise it would be secondary. So you can see here that an alkyl group still directs ortho-para. It is still an activating group, but as we discussed, it is a weak activating group because it does not have the lone pairs that can be donated, thus giving a fourth resonance structure. So this is the difference between the lone pair containing activating group and simply the alkyl activating group. Both of them are still ortho-para directors, just that one imparts a lot more nucleophilicity and more higher reactivity to the benzene ring. So let's look at the effect of an electron withdrawing group on the outcome of this bromine addition to our benzene ring. There are again three positions that we can look at, and I'm going to do the same analysis that I used on the previous example with the electron donating group. And again, I'm going to pause my video while I draw some resonance structures, and you can draw them at the same time. Check yours once we come back on, and we can discuss from there. So here are my three resonance structures that I get when I add bromine to the ortho position. And you can see that they look pretty standard. They have a cation at three locations in the ring, just like we had before. The interesting thing is that this one here has the cation on the carbon at the top of the ring, very close to this electron withdrawing group, which has a large delta plus at the carbonyl carbon. And so this actually has a destabilizing interaction because we have the cation in the ring very near to the large partial positive on the carbonyl group. We don't have that destabilizing interaction for these other two resonance structures, but we do have that here. So let's keep that in mind as we draw our next set of resonance structures. The next one, of course, is the meta addition. And I'm going to pause the video while I draw those structures as well. So here I have my 3 resonance structures resulting from meta addition of the bromine. And again, you can see the 3 cations as they move about the ring. The important thing to recognize is that none of these resonance structures have the cation on this position, thus avoiding this destabilizing interaction between the large partial positive on the carbonyl carbon and the actual full positive on the ring carbon. So that might make meta a little more favorable than ortho. So one more to look at, and we'll be ready to complete our discussion here. So again, the purple will be para addition. I'm going to pause here again and complete my resonance structures. Okay, so here are my 3 resonance structures for para addition. And you'll notice a very similar pattern, I think, to the ortho addition, where I have the 3 cations in the ring that move around the ring. This structure here in the middle, again, has that destabilizing interaction where the full cation on the ring is right next to the carbonyl carbon that bears a strong partial positive charge. So this, again, is destabilizing. So these 2 resonance structures that I underlined in black both help to prevent the ortho or the para addition in this case. So in this case, electron withdrawing groups, they deactivate the ring simply because they remove electron density from the ring, but they are also meta directors, because by adding substituents to the meta position, they are avoiding forming these resonance structures that have the destabilizing interaction of the full positive charge on the ring right next to the large partial positive charge on the carbonyl carbon. And if I draw the Lewis structure for a nitro group, you can see that if I were to put a charge on the ring right next to the nitro group, like I would see in say, this middle resonance structure here, now I have 2 positive charges right next to each other. This is not a partial positive charge, this is a full positive charge. So that's why the nitro group is even more of a meta-director and more of a deactivator. This is a very destabilizing effect, and so the nitro group, just like all electron withdrawing groups, will be a meta-director.